Good afternoon or good morning, depending on where you're calling in from. Welcome to the Alliance for Water Efficiency's webinar today on cooling tower technology and the study that we've been conducting recently. I want to thank you all. If we could have the next slide, please, Liam. I'm Ron Burke, CEO of the Alliance for Water Efficiency. We want to thank you all for joining us today. And I want to walk through just a few housekeeping items before we launch into the content and really dive deep into this fascinating study. We are shooting for 60 minutes in length, and we will have time for questions at the end. The audio is obviously through your telephone or your computer microphone and speakers. Hopefully you're hearing me just fine at this point. We will be muting the telephone, your phone line, I should say, during the presentation in order to limit background noise and to help improve the quality of the recording that we are doing today to make this webinar available on YouTube at a later date. However, we do want your participation. We really encourage you to submit questions as the presentation goes on. We will have time at the end for your questions to be answered by the speakers. I also want to encourage you to learn more about the Alliance for Water Efficiency. If you're not a member already, we hope you'll consider becoming one. There are numerous benefits to being a member, including access to the model that we'll be talking about today during this presentation, and a variety of other benefits. You can learn more at the link you see here on this slide. We are going to have a distinguished panel of speakers today who've worked on this analysis. Again, I'm Ron Burke, President and CEO of the Alliance for Water Efficiency. We'll be hearing from Brian Boyd with Pacific Northwest National Laboratory, Tyler Harris with the same organization, Maureen Erbeznik, who also worked in this analysis. Next slide, please. Rachel Waite with the Municipal Water District of Orange County, Sam Fetter with the same organization, and our very own Bill Christensen, the Director of Programs at the Alliance for Water Efficiency. It's a distinguished set of experts. I am really excited to hear more about this study. I know that we have a number of participants on the call today who are excited to learn more as well. With that in mind, I'm going to turn it over to Bill to walk us through the roadmap for today's webinar. Bill.
All right, thank you, Ron. This is Bill Christensen with the Alliance for Water Efficiency. And here's a roadmap of today's webinar, just to give you an idea of what we'll cover today and where we're headed. So I'm gonna discuss our cooling technology study, and then the Pacific Northwest National Lab will provide an overview of the cooling tower estimating model and the associated guide. And then the Municipal Water District of Orange County will talk about its experience using the cooling tower estimating model. And then we'll have time for questions after that. So next slide, please. So the origin of this study came from the AWE Research Committee, which is one of our member advisory committees that meets every other month to talk about ongoing research and also identify areas of needed research in our industry. And cooling towers were identified for multiple reasons. Probably first and foremost is that cooling towers are unfamiliar to most people. But it's also difficult to understand the scope of cooling towers in a water provider's service area. How many cooling towers are there? Where are they located? What's the water use and the savings potential of those cooling towers? So these are things that are not apparent, and this study aims to help our members figure those things out. It's also difficult to design effective water efficiency programs for cooling towers in terms of what strategies make the most sense in a given service area, who are the right people to connect with, and on and on. So there's just a general lack of resources and tools on this topic, and this study aims to improve that. And then this project is also very important because there's a large opportunity for water savings. Improving the water efficiency of cooling towers at one facility can generate hundreds of thousands of gallons of savings annually. So just huge savings potential. Next slide, please. So there are a lot of great people involved in this project. The Pacific Northwest National Lab is the primary contractor doing the research and developing tools and resources, but Maureen Erbeznik is also instrumental in this project and working closely with AWE staff to help manage the project and providing her expert guidance as well. We also have a project advisory committee that includes all of the project funders, as well as Bill Hoffman of H.W. Hoffman and Associates, who has been kind enough to lend his guidance and expertise along the way. Next slide, please. So I mentioned that the project advisory committee is made up of funders, and I want to give a huge thank you to all of the funders. This is a really big project, and it would not be possible without their financial support as well as their guidance. We have 18 funders, mostly in the United States, but we have 2 in Canada, and we look forward to meeting with them soon to discuss additional resources that are near completion. And just again, before leaving this slide, I just want to give a huge thank you. And so we can go to my final slide. So this is the Cooling Technology Study webpage on our website. It is located in our resource library in the commercial, industrial, and institutional section. And this is where we will post updates on the site. But I want to touch on the 5 main objectives of the study that you see there near the top of the page. And it's to develop best practices for identifying water-cooled facilities, as well as developing best practices for estimating the consumptive and non-consumptive water demands for cooling. And then we are going to determine, or working on determining, conservation potential for efficiency improvements to cooling towers, as well as looking at the savings potential for alternative cooling technologies. And when all this work is done, we will develop practical guides that incorporate the study results. So we're going to develop guides and outreach materials to help our members design or improve existing cooling tower programs and help make them more successful. We will announce all project resource releases through our normal channels, like our emails, but we'll also post them on this page. So the cooling tower estimating model, which is the focus of today's webinar, hits on a few of these 5 objectives, and you'll hear about that from the team. And so just before I wrap up, the cooling tower estimating model is an AWE member-only resource, and it can be requested through the AWE website. So if you go to this page, you see that link for the cooling tower estimating model. You follow that, and you can request a copy of it. So we encourage you to do that, and that's it for me, and I will turn it over to PNNL staff. Thank you.
Thanks, Bill. This is Brian Boyd. I'm a research engineer at Pacific Northwest National Lab. And we are, myself and Tyler, principally Tyler, are going to cover the cooling tower estimating model, or as we refer to it as CTEM. And our objectives are really are threefold. We want to try to give all of the audience an idea of what is CTEM, what it does, and how to use it as a resource. Go ahead to the next slide, please. Before we get into that, just a couple of kind of cooling tower 101 thoughts to share. Many of you may be very familiar with cooling towers, but if you're not, we wanted to just kind of hit on what they are. As the slide states, and has some pictures of a variety of different cooling towers, from some gigantic hyperbolic towers to some industrial towers, cross flow, and then also some in more of an urban setting in a city. They are a workhorse, and actually they rely on the efficient use of water, the natural qualities in water, to transport heat and to dissipate heat from either industrial processes or from comfort cooling purposes for our built infrastructure. Next slide, please. May have just a little lag. Yeah, and this slide actually illustrates, this is the campus where Tyler and I work. And at our own campus, we rely on evaporative cooling, and we have some traditional cooling towers. And then in the bottom right of that picture, we actually utilize an evaporative decoration feature of a water pond there to do some evaporative cooling for the main part of campus. Go ahead, the next slide. Yeah, and so just some cooling tower basics. The process, again, utilizes water's capability to transport heat from either a central building HVAC system or a large industrial process such as a power plant or refinery, and the water is transported to the cooling tower system where much of the water, where the BTUs are given up to the atmosphere through evaporation. And in that cooling process, then the cool water goes back to the tower basin, and it can go back into the process or the building HVAC system to gather more heat in return. And there's some natural things that happen. The dissolved solids that are in the water, they will concentrate, and so there needs to be a function of continual makeup water and then also blow down water. And so part of this, again, this effort was to try to aggregate across a large scale, a whole utility service territory to estimate roughly what is the heat load that needs to be dissipated, and how many cooling towers are there in that service territory, and then get into also some water quality considerations. We've broken it out into two different descriptors of consumptive and non-consumptive. Consumptive water is the water that goes up from the top of the cooling tower, the plume, and that would be given up into the atmosphere. The non-consumptive water would be the blowdown water, which would actually stay in the water into the service territory or the region. Go ahead to the next slide. Now I'm going to hand the microphone over to Tyler Harris, and he can get into the specifics of the model.
All right, thanks, Brian. Yeah, I'm a sustainability engineer at PNNL, and this was one of the first projects I was brought onto on the lab, and it's been a pleasure and thrill to be able to be a part of developing this tool. So thanks for this opportunity to present here. So the cooling tower estimating model, which we affectionately refer to as CTEM. So what it does is it takes, it looks at a utility service area, right? So we're looking at somewhat from a top-down high-level view. And so CTEM estimates the overall cooling tower usage in the area, which includes the number of facilities, the number of cooling towers. So as you can see in that picture there, there's more than one cooling tower at that particular facility. And then it estimates the capacity for that region of cooling tower capacity total cumulative. And then it estimates the use or the load. And then from there estimates the efficiency or the water use. And then looks at, based on water quality, basic water quality inputs, it estimates what we call the cycles of concentration, or the COC, and that is an efficiency where you can see a real kind of significant initial savings in water if you can improve the cycles of concentration. So the minimum, the task was to pull together from publicly available data a tool that you can, across the US and Canada, be able to enter basic information about the region, and then from that, high-level estimates of these cooling tower parameters are outputted. And so, and then there's additional features that come in after that, and we'll go over those. But the minimum inputs that you need to run the tool are just the country, and for now we're just limited to United States and Canada, the state or province. Then for US locations, you enter the county. And then you enter your service population. So your utility service area might not be the entire county. So you might put in the subset of the population of that county that you're interested in. And then you'll enter a water quality parameter. And we went with 2 high-level parameters for the base inputs, and it's either you can choose total dissolved solids or conductivity. Of all the base input information, that's the potentially the more difficult, but at the same time, it's generally pretty not too difficult to get your source water quality information, particularly if you are a water utility. So with those base inputs, the output estimates include the number of facilities within that region and service population with cooling towers, the number of individual cooling towers, the cumulative cooling tower capacity and load for that service population region. And then from that, based on climate analysis that we did that we'll discuss here momentarily, we get the cooling tower water use, and we have a functionality where you can adjust the cycles of concentration to see how much water savings you can improve by improving your average cycles of concentration for the region. And then also automatically generated is a large facility inventory. And we'll talk more about that. It's not meant to be a definitive that this list, every facility on here will have a cooling tower. Those were databases that we collected from across the continent and assembled, and we had to do a lot of assumptions and regressions to compile those. It's also a static list, but we'll get in a bit more into that. But one thing before we move on to some more of the details of the model is there's this famous quote by George Box that all models are wrong, but some are useful. So keep that in mind when we discuss this and the application of this. That it's not intended to give an exact perfect answer, but it's intended to help with the purposes of understanding cooling towers in a region, their use and potential alternatives and optimization for improved water use and potential energy use. So next slide. Okay, so here are a bunch of screenshots from the CTEM Excel tool. It is a macro-based tool, so you do have to enable macros, but otherwise it's all in Excel. And so down at the bottom, you can see a little clipping of all of the different available tabs. So some of the key ones here we have are the base inputs tab, where you can see it's just a handful of data inputs that you have to put in to do the basic functionality. And then once you run the model, it'll take you to the results estimate tab, where it'll output for the number of facilities, cooling towers, capacity, load, and water use for a subset of the large scale facilities, And those are the auto-populated large facilities that there's another tab for validation of those, but you can see in the upper right, the inventory tab, the items, the large facilities that are auto-populated in the tool are exported to an inventory tab. And then in the commercial facilities, that's based on regressions that we'll talk about, and then it sums those values for the total region. Also included in the CTEM is an example calculation tab. And the example region that's used in that example calculation is the same region that we'll look at shortly here. There's also an overview tab and some of the other tabs we'll get into as we go. So next slide, please. Okay, so for the example that we used, we chose we basically wanted to choose a somewhat neutral location, and so we chose a suburban county in Michigan, Oakland County. And so you can see in the top right that the United States, Michigan, Oakland was entered, and then circled there in blue is the population in county 2018. So that's automatically populated once it's filled in down to the county for US counties. And that's for a reference. So let's say you want to just use the whole county. For the enter population served, you would enter that entire number. For this example, we just rounded down a bit and used 1.25 million for the population served. And then you can see for the highlighted in the red circle of the IECC climate zone 5A. So zoomed in on the lower left, you can see a larger star there. That's roughly where Oakland County is. And you can see the 5 and the moist A circled. So that 5A is automatically populated for the user reference. And then the map is also on that page. So you can verify that it's the correct climate zone for your region. Then you can see the select water quality measurement type. That's a drop down where you can, and the United States, the country, state, and county are all drop down menus, as well as the measurement type. So here we selected TDS, and we just took kind of a mid-range TDS of 500 and ran it. So next slide, please. So getting a bit into how this all comes together, we broke down the regions by the IECC climate zones. It's used by a lot of different, it's pretty much a standard tool used in buildings and energy systems. And we use the Federal Energy Decision System, or FEDS, to take a standard building and run its annual cooling load by hour for all of those, for 12 different climate zones, representative climate zones. And so you can see on the lower right, the 12 different plots. And what you're seeing, there's no bottom axis there, but basically that's January to December throughout the year, and it's hourly. And the left axis, you're looking at the cooling load for that standard building. So that same building moved around to all those locations, and you can kind of quickly look and see, okay, how much what the loads are and how much they're used at different points in the year. So, looking at Honolulu, you can see it's pretty much used pretty consistently throughout the year, where Fairbanks, Alaska, right, certainly cooling loads, but it's, just for the summer months. And the figure at the top shows how the cooling load relates to the regional temperatures as well. So next slide. I'm sorry, it's 16 regions, not 12. I think I said 12. So this is kind of a illustration of some of the output results that we got from all those feds runs that we used for our modeling. And so all of those different locations, this plot in blue, that is the annual load. So how much the total, essentially that's the heat rejected, the total heat rejected over the course of the year. So, you know, in Honolulu and Tampa, Florida, a lot of heat rejected throughout the year, where in Fairbanks, Alaska, the blue, it's not so much. The red triangles, and that's on the right side, that's the peak cooling load. So when they're using the cooling towers, or basically in their hottest time period of the year, what the load would be at those different regions. So you can see that proportionately it's a bit different than the total amount that they're used, right? And so we use that information to help us determine a duty factor, or how much the cooling tower is used per year relative to its total capacity. And so those numbers are in percentages are illustrated in light green at the bottom of the blue for the different regions. So for this example in Michigan, the representative region is 5A, and there it's 9%, but it's 8.8% you'll see in subsequent slides for the duty factor. So next slide, please. Okay, and so that was the feds that we used there. For the other so publicly available data that we used for CTEM include the CBACS, the Commercial Building Energy Consumption Survey, the U.S. Census Bureau, and the New York State Department of Health. And to the right here, you can see some of our analysis that we used for CTEM from the CBACS database. And so what you're seeing here is a heat map of using the CBACS data, showing the likelihood of buildings of that type. So on the left side, you see number of floors. On the bottom, you see square footage. So the lower left, those are lower, smaller buildings. As you go up and to the right, those are taller, bigger buildings. And so here you can see that the green indicates more likelihood of having water-cooled chillers and a cooling tower. So that what you're looking at there is for all building types, but kind of behind that figure, you can see a bunch of other plots. There are numerous different building types defined in CBACS, so we did that same calculation for all the different building types, and the set that were most likely to have cooling towers we built into the model that we'll look at a bit later. So next slide. And this is, I won't talk much about this, but this is just an example of some work we did with the census data, looking at correlations between industry labor types and overall population. And so this helps us because, so like you can see, education and health on the left there, and the correlation with population is you know, really high, 0.97 R². And so that indicates that you can pretty much say a region with a higher population has a higher amount of workers in education and health. which then means that there's going to be a larger number of buildings that are dedicated to education and health. And education and health buildings, particularly health and hospitals, are more likely to have cooling towers. And so this kind of is a step in that kind of linking process between all of the publicly available data. Next slide, please. So we're going to get into the CTEM base functionality here. So these couple of clippings here should be looking a little bit familiar to you at this point. So the one on the left there is the base inputs tab. So the Michigan, Oakland County, Michigan information's put in there. And then once it's put in, you click that estimate results button and it'll take you to the results estimates tab there in the middle. And those are results. There's a little timestamp at the bottom there. It's a little small, but that basically says information of the input information. So then up there at the top, you can see the duty factor 8.8. Like I had mentioned before, that came from that Fed's data analysis. And in a little bit further, you'll see that that's adjustable. We have a feature where that's adjustable for a variety of reasons. The base kind of estimate for that duty factor for the overall region, it might be slightly different, and you might have knowledge about that and might want to adjust that. So that's a feature advanced feature that we'll get into. So you can see for this the service population of 1.25 million suburbs of Detroit in Michigan, that it has 30 large-scale facilities that it identified, which so hidden kind of behind that to the lower right is an output tab that we'll get into a little bit more later. But that shows those 30 different facilities there that were auto-populated for the large-scale facilities. And then, so in that center clipping again, the commercial facilities, so that's where all the regressions and data analysis comes in. And so for that climate, that particular community with their census incoming workers, the different industries and labor forces, we were able to estimate that there are approximately 515 facilities in that region that have cooling towers. So put together, 545 estimated total facilities in that region. And so similarly, you can go down and see a number of cooling towers. So in general, this changes slightly from region to region, but in general, there's about 2 cooling towers on average per facility that uses cooling towers across the country. But that ranges from different climate zones and different demographics. And so it ranges in the model between something like 1.5 and 2.5. But so there you can see it's about that, scale of 2 factor between the number of facilities and number of cooling towers. And then the cooling tons, the capacity in tons, cooling load in tons per year. So that's basically an indication of the energy rejected by the cooling tower per year. And then from that, you can estimate the consumptive water use, because that's a direct connection to the amount of heat rejected. And then based on water quality entry, you can estimate the non-consumptive or blowdown water use. And then those summed together are the total water use. And then we, of course, because these are estimates, we included some ranges there for those water uses, and we also have, we know that some utilities use acre feet as a common measurement, so we have that in there as well. Next slide. Okay, so this is a clipping of the auto-populated large facility inventory output. So this again is automatically generated from those base inputs, and based on the CBACs and other analysis, as well as what data on the different facilities we could get our hands on publicly. The facilities there on the lower left, those are the ones that we were able to assemble databases for regions across Canada and the US. So for this region, you can see that there were 30 facilities, and there were a couple of college universities, dozen or so data centers and hospitals. Next slide, please. So now getting into a bit of the advanced features, you can go in and customize that list of the auto-populated large facilities. So this is a clipping of the tab where the user can go in and customize and validate the list. And I had mentioned earlier that just because that this a facility is listed here doesn't indicate that we have confirmed that there are cooling towers there. We weren't able to do that for the thousands and thousands of buildings in the data set. These were just the facilities and locations that were most likely to have cooling towers, and then we were able to get a proxy for the different building types. Like for example, for college universities, it was the number of post bachelor enrollees, so kind of graduate students. And so we found a subset of colleges and universities where we had cooling tower information, capacities, loads, and number of facilities. And so we were able to correlate those facilities with the proxies and then make an estimate for all of the other entries in the list. So we did something similar for all of those. So you know, so this allows then for the user to go in and, first of all, your service territory might be smaller than the overall county. And so in here, you can see that there's multiple cities listed there. And so you could go in and deselect all of the ones that aren't in your city. And then as you go in and validate the ones that are, you can, if you find one that doesn't in fact have a cooling tower, you can click the no, and then run the results again, and it'll update the output results kind of clipped in that lower left, showing the large scale facilities there. So then also you can add, so this is a static list. So down at the bottom of this, you can add additional large facilities. However, in order for it to be included in the overall estimate, you have to enter a estimated cooling tower capacity in tons, the row to the right there. We also added a feature at the top right of that tab there to help kind of do a very high level estimate based on visual inspection of that facility, what the cooling tower capacity would be. So next slide.
Hey, Tyler, this is Bill. You've got about 7 slides left and really just a few minutes. So if you could move through them
Sure.
swiftly, it'd be appreciated. Yep. Thank you.
Yep. And so this is another optional advanced feature where to help kind of build an inventory. So if you have real property or commercial data, basically the building type, and the square footage are the mandatory pieces of information. If you have the number of floors as well, it gives a better inference. But when you enter that information in here, it infers whether it's likely to have a cooling tower. And then similarly, the user can go in and customize that. And then go to the next tab, please, or the next slide. Okay, so these are, this is kind of a bunch of different advanced features. We'll go through these, skip some of them, but can you go to the next slide? Let's see. So as I had mentioned, that one of the key ways that you can conserve water in cooling towers is by increasing the cycles of concentration. And so CTEM estimates a baseline based on the water quality information entered. And then in this little clipping here, it takes that baseline and adds 1 to it and shows you what the potential savings would be by adding 1 cycle of concentration. But both of those numbers are adjustable. So let's say you think you can bring it up to 5, you could change the potential to 5. Or let's say you're pretty sure that your average is 2.8. You could enter 2.8 in the top there, and then what you want to bring it up to and see the savings potential there. But so for this example here, you can see that by increasing cycles of concentration from a baseline of 3 to 4 would save 156 million gallons per year in the non-consumptive water, or 33% of the non-consumptive water use. Now there is a kind of a barrier in terms of efficiency. So in the lower left there, you can see that as you increase the cycles of concentration kind of past 7, 8, 9, your return on water savings decreases. So really, if you're in the 1, 2, 3s area, minor increases make a huge increase in your savings, whereas you get up to 5 and 6, you get less of a savings by increasing. So you're looking to get things from like 2 to 5. It would be a huge benefit. Next slide. Okay, so here's where that user input once you check those, or you run it and you can validate them. And so there were 7 facilities identified as likely having cooling towers in the user input. And so you can see that on the inventory output page at the top there, it shares some of that information. So that's 7 facilities there. And then you can see down below, it also exports that information. And then on the results tab, there's an area where it does some statistical estimates of the user inputted inventory. And that's basically compared to the commercial inventory. And so the idea is that as you kind of build up your user input inventory, you can see how close you are to the estimated total number of facilities in the region. So for this inventory, you have a long way to go, about 1% of the facilities located. Next slide. So again, this is the duty factor. So this is more on the consumptive use side of things. But so that similarly, there's a section where you can adjust the duty factor. Next slide. Yeah, so that was a quick overview and summary of the CTEM, or the cooling tower estimating model. And we hope that, we know it's not going to give exact answers, but we hope that it's useful. Next slide, please. There is a guidebook that accompanies this, and I won't go into this much, but I would recommend you check it out if you're able. It gives a lot more information on kind of identifying cooling towers and the background to all of this. And next slide. And we're still working on this stuff. We're adding additional water quality features. and also on some of the other tasks doing market penetration and savings potential over time. So we look forward to sharing more as we go. And I think that wraps it up. Thank you for joining, and sorry for going over on my time.
All right. Well, thank you, Tyler and Brian, for that great overview of the cooling tower estimating model. We can go to the next slide, and we'll be hearing from the Municipal Water District of Orange County on their experience using the cooling tower estimating model. And it does look like we may go a little over time. So I want to remind everyone that this is recorded, and we'll have the recording available for viewing later if you have to hop off at the top of the hour. So please do get your questions in, and we'll answer them during the webinar. But if we go too much over time, we'll make sure we get all questions answered and sent to you. So now I will turn it over to Rachel and Sam.
Thank you, Bill. Hi, everyone. My name is Rachel Waite. I'm a water use efficiency analyst with the Municipal Water District Orange County, commonly referred to as MODOC. And I also have Sam Fetter here with me. Sam is a water use efficiency intern with the district, and he has played a really important role in what MODOC has been doing with the CTEM model. We are going to be speaking about our effort to use aerial imagery in validating the presence of cooling towers that were predicted by the CTEM model. Next slide, please. First, I'll start off with a little bit about MODOC. We're a regional wholesaler for most of Orange County. We are governed by a 7-member board of elected officials, and we have 28-member retail agencies shown here on the map. Orange County has a Mediterranean climate. Our biome is characterized by chaparral and coastal sage scrub, and since I'm a geographer, I always love to share my favorite fun fact, which is that we are located in a biodiversity hotspot. Next slide, please. So what MODOC really focused on here was taking the auto population list from the CTEM model and using aerial imagery to validate the presence of cooling towers. In just a moment, Sam will speak about how he went about doing this. But first, I just want to make a few comments on the spatial distribution of the predicted towers. You'll notice the orange points, those are representing the predicted towers. They're clustered in the most urbanized parts of the county. Northern and southern Orange County have some pretty different socioeconomic and land use demographics, and there is much more industrial space found in north central Orange County. So as a Orange County native, I think if I were to try to predict where towers would be, I think my map would line up pretty close with this. So my first takeaway of using the model right out the gate was that I feel like the distribution here was pretty spot on. Next slide, please. So as I mentioned, what Sam was working on was using aerial imagery to validate the presence of a tower. So now I will turn it over to Sam to share his experience in doing that.
Thank you, Rachel, and thank you for everyone for having me. I'm excited to be here. So on the left here, you see we have sites that are confirmed positive. So the auto-populated list predicted that they had a cooling tower, and in fact they did. This one on the top left, it's a bit hard to see. You have to follow this red arrow, but there is a small cooling tower down on the side of that building. You may need to zoom in or look at it from an angle to see it clearly, but it's there. On the bottom, you can see some very clear cooling towers. This is actually at Disneyland right next to the Space Mountain ride. Even from a distance, they're large, they're out in the open, very easy to spot. On the right, we have some false positive sites. So this is fairly common in the auto-populated list. You'd have a small site, maybe only one level, small industrial building, labeled as something to do with electronics, tech, or data. And it would just have these rooftop units on top, the RTUs, and no cooling tower around. So that was fairly common that we would see that. And one thing that is important is these pictures are both the same building. The top is Google My Maps zoomed in. The bottom is the 3-inch imagery from Eagle View, and you can tell the bottom image is just much clearer, easy to tell what those rooftop units are, and you can see the sides of the buildings, which was really crucial for the sites that had a really small cooling tower or didn't have a cooling tower present, to be confident that you're marking it as not having a cooling tower at all. This 3-inch imagery was just basically essential for those sites. And I'll send it back over to Rachel.
Thank you, Sam. Really great work on that. Next slide, please. So here we have the results of our validation effort. There were 463 sites in total. Sam was able to confirm about 17% of them, and was able to not confirm the presence of a tower on about 75. There were some where it was a bit hard to see, so we do plan to revisit those sites. They're a bit tricky. Sometimes there were large vegetation, like large trees, kind of blocking the perimeter of buildings. And then on the right, you'll see a breakdown of those results. And these were categories that were assigned by the model. So you'll see an airport, that site was confirmed. In terms of college and universities, almost 70% of those listed as colleges or universities were confirmed to have a tower. Those that did not were smaller community colleges where they just didn't quite have the large buildings that a typical larger university would. In terms of data centers, almost 30% were confirmed, hospitals 60%, and those that were not confirmed were smaller, usually like an outpatient clinic, a smaller building. Some sites were classified as other, and we did not find any towers in that other category. We do plan on investigating that a little bit more and trying to break down what type of sites were classified there. And then some did not receive a classification, and that was about 12% confirmed for that category. Next slide, please. So on this slide, we have the map on the left, which shows the validation results that were on the previous slide. And on the right, a map that was created using the user input feature. And these are sites that were inferred to have a tower by the model. And you can see that the spatial distribution of these points are pretty similar. The user input list actually identified a bit more in southern Orange County, but in general, the distribution was pretty similar. And MODOC worked with Maureen Erbeznik on this to create our user input list. And on the next slide, she'll speak a bit about how you can build that list. Next slide, please. So just before I hand it over to Maureen, I'll just give a brief overview on this slide. These are a few trends that we noticed. As Sam mentioned, for the false positive, some of the buildings were smaller buildings that had a rooftop unit. But another thing that popped up were oil fields or large industrial lots that were undeveloped. And we have a few examples of those on the left there. And then on the right, sites that we were able to identify through the user input list tended to be larger buildings with more stories, like a big bank or a hotel. And we're still working through this list, but about 60% of those sites that we've gotten through have been confirmed to have a cooling tower so far. So I will hand it off to Maureen to talk about the user input list.
Thanks, Rachel. Great presentation. The main point I just wanted to highlight here is that the user input list is really critical as you're building the inventory, and where you get it is imperative. We actually use the CoStar list. It's a real estate database, and it had the square footage, the building type, which we had to crosswalk with the building types in the model. And then it also had the number of stories. So we had a much better, more precision in inferring whether or not a cooling tower was at the property or not. So that's hence the 60% of them having are included in the actual inventory. When you're looking at the auto-populated list, these are just databases that we collected or PNNL collected during the process of building the algorithms. And those ones, we don't have the actual square footage of the buildings or this or any, so there's going to be a lot more false positives in that data. But it's just the beginnings. It's just a starting place for people. It's a good place that you just begin to build your inventory, know how many hospitals, colleges for any of your conservation programs. So just wanted to highlight that. There's a lot more guidance in the actual guide on how to get real property data. You can go to the assessor's office, your planning departments, your and real estate databases are probably the best and most accurate. So I'll turn it back over to you, Rachel.
Great, thanks, Maureen. And we can move on to the next slide. So final thoughts and takeaways. This is really amazing information. The information provided by the model is really valuable. So a huge thanks to AWE, PNNL, and Maureen on this, because it's really fantastic stuff. There's so much that can be done with this type of data, but some things that MODOC is looking at is to be able to share this information with our retail water agencies and work on some targeted marketing. Additionally, we can use this to better understand CII water use in Orange County, including industrial usage portfolios, efficiency potential, and use it for resources planning. Additionally, those water savings estimates we can couple with an incentive program called the Water Savings Incentive Program that is ran through Metropolitan Water District of Southern California. And that incentive is based on savings. So this can be a great tool in trying to market that program to these sites. And also, even outside of that program, it can help calculate and kind of pitch return on investment to any potential sites that are targeted to increase efficiencies. So again, just really great stuff. We're finding this to be extremely valuable. That wraps it up for me, so I will turn it back over to Bill. Thank you.
I'm actually turning it over to Ron. Hey, thank you, Rachel. Thank you to all of our speakers, Bill, Tyler, Maureen, Rachel, Sam, Bill, amazing. I think we all learned a lot today, and we're excited about the results and the ability for this model and the other processes we discussed today to kind of help us really tackle and advance efficiency in the context of cooling towers. So thank you, everyone, for your contributions, and for those of you who participated and listened today. Let's see. I know we've got some questions, and I'm going to continue to submit your questions. That's one thing I wanted to say right off the bat. We're going to, again, record this. If you have to sign off, we'll be answering the questions after you do. This will be on YouTube at a later date. We'll be sending you the link for the webinar, as well as a PDF with some information. Stay tuned for additional information from us about upcoming webinars sponsored by the Alliance for Water Efficiency. You can check out our regular news updates at our website, allianceforwaterefficiency.org. And again, please consider becoming a member. You'll get access to this model and a number of other great benefits. While joining North America's leading network of water efficiency leaders, we'd love to have you as a member if you're not already. I'm going to turn it over to Liam to share questions we've received so far.
All right, thanks everybody. Let's jump right in. First question, can the model allow for more than one county to be an input if the service area covers parts of 2 different counties?
Yeah, this is Tyler from PNNL. Great question. I'm sorry, I meant to mention that earlier. No, the current version of the tool doesn't in itself allow for multiple counties. So what we recommend is for you to run multiple instances of the model if you have multiple counties that your service territory covers. Or conversely, well, yeah, that's the recommended approach at this point.
All right, great.
And then
thank you, Tyler.
compiling the results together.
Awesome, thank you. Hold on just one sec. Next question, for service population, can you confirm that that would be functional population as opposed to residential population only? Not sure who would be best to answer.
Yeah. Can you ask what was the functional population?
Yeah, for service population, can you confirm that would be functional population as opposed to residential population?
No, actually, and it would be, this isn't my expertise on this particular thing, but basically that's would be the residential population. The model itself takes into consideration, you know, the commuters, incoming, outgoing, and different labor forces, but that input there is just the residential population. And yeah, that's a good thing for us to make sure to emphasize in the future.
Okay, thank you. Have CTEM result estimates been cross-checked with actuals in certain areas to confirm the accuracy of the model?
This is Brian. I'll answer that question. Yes, we've gone through this, the results with a couple of the utility partners, and we're very grateful for that, and appreciative of MODOC being willing to step forward for this webinar, also to give us useful feedback. A lot of the underlyings that went into the calculations were built off of the New York database, which was really thorough, but we did have the opportunity in some of the early beta versions to partner with some of the funding utilities and validate the results.
All right, thank you, Brian. Somebody's asking about where the model is available, and it is available on the Alliance for Water Efficiency's website, and I can go ahead and send it out to all of the attendees when I send the recording and the webinar PowerPoint, so be on the lookout for that. And the next question is, for the input, where do you find the water quality, for example, total dissolved solids or conductivity info?
This is Brian. I'll answer that question. That's a really good question. If you have, oftentimes you can find that data in some of the water quality reports, but that can also be a little bit tricky because there may be seasonal variations. I know in Southern California there's blending. Like for Southern Nevada, they really get their source water from 2 locations, and it didn't really take much to drill down, and you can find detailed information depending on the source. So it might be a question to go back to some of the actual water utility sites or points of contact. USGS has detailed information, but I'll caution you, sometimes that's pre-layered and you need to know what you're looking for. But I think in general, asking somebody within the water utility who might have that information or looking at water quality reports and doing a drill down from there will be your best place to start.
And I'd also say that a first place I go to is your internet search provider and search for TDS or conductivity and your region. And you might find a water quality report that gives you your number right there. So that'd be my first place to look.
All right, thank you. And actually only one more question right now. We'll see if any more trickle in here, but someone's wondering, did MODOC show that model had 75% of their sites as a false positive?
This is Rachel. A little less than 75%, but yes, that from the auto-populated model, that is correct. When we transferred into using the user input model, that accuracy has shot up to 60%.
All right, and that is actually it for questions. So if anybody thinks of any after the webinar, feel free to go ahead and reach out. Oh, looks like one more is coming in. What source did MODOC utilize to identify self-reported sites?
The CoStar.
Probably.
Yeah. Oh, sorry, Rachel.
Oh no, I was gonna hand it off to you. So please go ahead, Maureen.
We purchased a real estate database called CoStar, and it's fairly expensive. You have to pay an annual fee. So it's just something, you know, it's one option to look into. Your assessor's office, the local county or city building and safety and or planning may also have databases if you have relationships with them. Basically, you need building type, square footage at a minimum.
All right, thank you. And looks like now we're officially done with questions. So as I was saying, if anybody thinks of any questions later on, feel free to reach out to me and I will make sure I get them to the appropriate speakers.
Okay, thank you, Liam. Thank you again to all of our speakers and for all of you for listening in today. Keep an eye out for an email from Liam with the link to the recorded webinar as well as some additional information. Check out the Alliance for Water Efficiency online. And again, we hope you'll consider becoming a member and we look forward to seeing you down the road. Thanks so much, everyone.
Thanks.